So good morning, everyone. So it's, as the director of São Carlos Institute of Physics, we have the pleasure to welcome Professor Anne Laurier. So I thank her very much for giving this lecture for us. As you know, this lecture is being organized by the SPIE student chapter in our institute, so I'll hand on to them to make the presentation.
Thank you.
Yeah. You just started. We were frozen a little bit.
Bom dia. Good morning. Actually, good afternoon for her. But so eu vou falar em português um pouco, o começo. Claramente ela vai falar em inglês. Queria primeiro falar bem-vindos para todos vocês, assim como obrigada por assistirem uma das nossas palestras da SPIE. Hoje temos uma palestra muito especial, né, com a professora que ganhou o Nobel pelo desenvolvimento e estudo das técnicas de física de atossegundos. A gente da SPIE quer também dar alguns agradecimentos. Queremos agradecer à diretoria do IFISC pela ajuda na organização, pela disposição dos equipamentos, as pessoas da área técnica, pelo som, ajuda com toda essa parte da organização. Especialmente queremos agradecer ao CEFISC, que tem organizado essa semana toda para vocês e ainda deu espaço para nós conseguir apresentar a palestra da professora. Quem mais? Professor Anderson vai estar com a gente no Zoom. Professor, muito obrigada por aceitar o convite. O professor Anderson, ele foi antigo companheiro de laboratório da professora Lund. O professor Lino também vai acompanhar a gente, vai ajudar. E o último agradecimento, para fazer esse agradecimento, eu queria definir, né? A SPIE, Student Chapter, né, é um grupo de estudantes aqui no Instituto de Física de São Carlos, que a gente é patrocinado, digamos assim, né, pela Sociedade Internacional de Ótica e Fotônica. E no nosso grupo, o que a gente faz é divulgação da ciência focada especificamente em ótica e fotônica. A gente está aberto para todos os estudantes que quiserem formar parte, que quiserem aprender com a gente. A gente faz vários eventos. Esse aqui é SPIE Talks. A gente tem diferentes temas. Temos também o Ciência por Elas, que vai acontecer no mês que vem. Além disso, a gente também tem os extras, né? Agora, os estudantes da graduação precisam de participação nos extras, podem vir para o chapter, formar parte dessa aventura com a gente. Então, muito obrigada, especialmente à gestão anterior e à nova gestão do chapter. Obrigada a todos, presidente, vice, Rafa e a professora Cristina, nossa prof do chapter. Sejam bem-vindos. Vou deixar a palavra com o professor Anderson. Thank you very much.
Okay, thank you very much. And it's a great pleasure. Can you hear? It's a great pleasure and great honor to be here and to see all of the students in the auditorium. Is full. I have been there in São Carlos a few times, and right after the Nobel Prize was announced, I went. I gave a talk about this, of course, general, without the nice details that we're going to hear. As you know, I had the great opportunity of work with Anne at the very beginning, and got her PhD in '86, and she started immediately working at the CEA in Saclay, and that's where we met. I went there through a collaboration, French-Brazilian collaboration. I went 3 times each year for 1 month, and I was quite lucky to learn. I thought I had learned, but I was not understanding all the theory, and would explain many times. And Gerard Monfray, Claude Moniz was a fantastic team. I learned a lot, and I helped with all the system. We have I co-author with them, with the group, 2 publications, one in the system and the other one in the physics, look at the high harmonic generation. I think it was the second big system in the world, the one in Saclay. But then after that, I followed my way and moved in '95 to Lund, where 2 years later she became a full professor, and she's there since. It's a big group, and then all the work that was when I talked to the students before, I mentioned how to someone who pursued something without having the objective of anything, but learn and contribute to an area that became a very important field, and it's now ready to go into technological phase and so on. So she has had many prizes, but she's a member of the Royal Swedish Society, Academy of Science since 2004. And then one of the many important prizes was the Wolf Prize in Physics in 22, and of course the Nobel Prize in 23, with Pierre Agustini, which is also a very good colleague that was in Saclay at that time. And I remember Pierre coming to the lab many times. How is it going? You have progressed, you have good results, new results. I remember well Pierre coming to the lab, and then and also Ferenc Krauss, which I do not know personally. So it was a great time. And when the Nobel Prize came out, some journalists talked to me, and one of them was very interesting. He asked, "Okay, I don't want to know about the physics. I want to know about the person." And I told him a story that I told the students, that we worked hard, and exactly it's very strict. I mean, we had time. We started at 9, 5 before 5. There was a bell. Everybody had to leave, and we were taking data. And one day it was a holiday, and we had to stop. And then we said, "No, we have to do something," and talk to the director. And he gave us a special authorization to work holiday and Saturday. I mean, that was someone that was just finished PhD and was eager to do things, and it was a fantastic time. So I don't know, perhaps someone is going to talk after me, but it's a really great pleasure to see you at least now in 2D, and hopefully we meet in person here in Brazil or some other place, and all the students will really enjoy a fantastic talk. Thank you very much.
Thank you. Thank you very much. It's nice to see you again.
Yes, good to see you.
Okay, do you see my slides? And you can hear me? Yeah.
Yes.
Yeah. Just from I think. Okay, I think you can start. Yeah, because no one is talking. So yeah, sorry.
Okay. So I can start. So this is the outline of the talk. First, I would like to talk about high-order harmonic generation, which was the start of this research, and then attosecond light pulses, and then very briefly applications. So nothing of what I'm going to tell you would have happened without the invention of the laser in 1960. This is a picture of Theodor Meinmann with the first laser, which was a ruby laser. So the invention of the laser led to a new field of research. One of them is nonlinear optics. And here you have a picture of the first experimental setup where second harmonic generation was observed. And you can look at this setup. You have a laser This is the first laser, the ruby laser, focused with a lens into a piece of crystal of quartz. And then you look at the radiation that is emitted using a prism. And then you have a detector, in this case, photographic plate. And in this experiment, they could observe for the first time a generation of new frequencies of light by interaction between the laser and the quartz crystal. So here it's second harmonic generation. Another field which was open thanks to the invention of the laser is what we call atoms in strong laser fields, and in particular multiphoton processes. Here you have an example of a two-photon excitation process, and these were processes actually predicted theoretically already in 1931 by Maria Goeppert-Mayer. You can also ionize atoms or molecules by absorbing several photons. Here is a multiphoton ionization process, and these were pioneered by actually Russian scientists in the 60s. In 1979, Pierre Agostini and his co-workers observed what is called now above threshold ionization. So it's multiphoton ionization, but you see that it's possible to absorb one more photon than what is strictly needed for the ionization. And you can observe these processes by looking at the energies of the electrons. My thesis work, this was in the 80s, was to study multiple ionization processes by multiphoton absorption. And here you have, for example, the double ionization of xenon atoms by multiphoton absorption. So at that time, it became clear that when you expose atoms to a strong laser field, you create ions. We create excited atoms, excited ions. It would be interesting to look at the fluorescence from these excited ions or excited atoms. So we set up an experiment where the idea was to look at this fluorescence light. And here is so this was at that time I had been recruited at the Commissariat à l'Énergie Atomique, this research institute in France, in the group of Gérard Mainfray and Claude Manus. And so we set up an experiment where we focus a laser into a gas of atoms, and then we analyze the radiation with a grating. Then we have a detector. So very simple setup, very similar to the one I showed you before about second harmonic generation. And I'm now showing you pictures of the experimental setup at the time. I'm not going to describe this in details. On the right, you have a picture of the laser, which was neodymium YAG laser, 40 picosecond pulse duration. You can see the oscillator between the two mirrors here. The laser is here, and then you have two amplifiers at the back. And this is the experimental setup. The laser is coming from the right. This is a vacuum chamber, and inside you have a grating and a detector, and we were also looking in the perpendicular direction. We also installed a grating and a detector. Why did we look at the perpendicular detection? That's because this fluorescence that we were trying to observe is emitted in all directions. We never saw anything in the perpendicular detection, and we actually didn't see much of the fluorescence. Instead, we saw radiation really directed along the laser propagation axis and made of high-order harmonics. This is one of the first results obtained in argon gas, And what you see here are peaks, and the number indicate the frequency is equal to an integer time the laser frequency. So 15 here means 15th harmonic. Frequency is equal to 15 times the laser frequency. So we observe this high order harmonics only odd order. This is because of the symmetry of the interaction, which is a symmetry relative to the origin. And this was really a surprise, especially if you look at the distribution of these high order harmonics. We find that it decreases for the first orders, but then there is a plateau behavior where all of these harmonics have more or less the same intensity, and then there is a cutoff frequency here. And why was it a surprise? It's because we were thinking very much in terms of perturbation theory, and in perturbation theory, you would like to write the polarization induced in the medium as a series in powers of the laser electric field. And for such a series to be valid, you need the first order to be much larger than the third, much larger than the fifth, etc. And this was obviously not the case when you look at this plateau behavior. So I think this was really the discovery, is this very high order harmonics and with this plateau behavior. How do we understand this phenomena? First of all, you need to consider really two areas in physics. One is atomic physics or quantum mechanics. How does the individual atoms interact with the laser field, and why do they produce all of these harmonics? This is described by the Schrödinger equation that you see here for an electron in an atomic potential, and then you have the laser atom interaction here written within the dipole approximation. But you also need to consider the many atom response, the response of the medium to the interaction. And this is part of electromagnetism. It's a Maxwell equation, which can be simplified going to a wave equation, as you see here. So here you describe the generation of a field due to the polarization in the medium due to this laser atom interaction. So what needs to be achieved to observe this high order harmonic generation is what is called phase matching. You need all of the atoms in the nonlinear medium to emit waves which are in phase. So this is what is called phase matching. So you have this double aspect that I thought was very interesting, this quantum mechanics and electromagnetism, atomic physics and nonlinear optics. And the first attempt to describe theoretically this phenomena was actually to solve numerically both the Schrödinger equation and the wave equation, which we managed to do at the beginning of the 90s. Doesn't mean we understand the physics of what is going on. I will come to that later. So around this time, there was really a huge progress in laser technology. You had three new laser inventions approximately at the same time. You have the discovery of chirp pulse amplification by Donna Strickland and Gérard Moreau. They got a Nobel Prize for that in 2018. You have a new material for laser, titanium sapphire, discovered by Peter Moulton. And then you have also a new technique to produce very short laser pulses called Kerr lens mode locking. So in Sweden, you have 3 scientists that you see here that decide to put together this new inventions and to build a new laser system in Lund called the Lund Laser Center. And they build and purchase the first terawatt laser system based on titanium sapphire in Lund. In parallel to this laser progress in Saclay, we built a dedicated instrumentation for the study of high-order harmonics. This is a picture here of this setup. I don't know if Anderson remember that, but so this is myself, my first student, Philippe Balcou, and then my second student, Pascal Salier. And we built this setup that you see here. It's basically very similar to what I showed you already. You have a lens. The laser is coming here from the left. It's coming through the wall here. There is a gas jet that you see here. You have optics to analyze the radiation, which is in this vacuum chamber. And then you have a photon detector, which is here, an electron multiplier, which is here. And at that time, we were using a neodymium glass laser to generate harmonics. The pulse duration of that laser was 1 picosecond. That was good. But the repetition rate of that laser was terrible. It was 1 shot per minute. And this is the time where the Swedish scientist called me and asked me, would you like to come to Lund to do experiment with our brand new titanium sapphire laser system? And of course, I said yes, I would like to do that. So actually, we sent this instrument that you see here in a truck, and myself and my students came to Lund to do experiments. And so look at the difference between these 2 laser systems. This titanium sapphire laser had a pulse duration of 200 femtoseconds and a repetition rate of 10 Hertz, which was really much, much better. And here I'm showing you one of the results that we obtained in Lund in 92. This is a harmonic generation in helium atom, and you see a beautiful plateau ending up with a cutoff here. The highest harmonic that we see is the 93rd harmonic, so really very, very high orders. And 2 years later, I actually came back to Lund simply for private reason, because I met my future husband in Lund and could get a professorship position in 97. First a position as associate professor in 95, and then as professor in 97. Now I'm coming to the second part of this talk, which is about attosecond light pulse. What is the connection between high-order harmonics and attosecond light pulse? So let me explain to you the connection on a cartoon, which is shown here. Here I'm representing 3 harmonics, 17th, 19th, and 21st. So they have slightly different frequencies. Let's assume that these harmonics are in phase at a certain time. The maxima here coincide. And then because of the periodicity of the process, this is 1/2 laser period, then the minima will coincide here, and then again the maxima and the minima, etc. Now let's sum these 3 harmonics. What do we get? We get a series, we call that a train of very, very short light pulses, simply by interferences of these harmonics. Here we have constructive interferences when they are in phase, and then destructive interferences when they are out of phase. So the light is really confined into very short light pulses, and we are in the attosecond range. Half a laser period of titanium sapphire laser is 1.3 femtosecond. So here we reach duration of the order of 200-300 attosecond. So what is represented here is the intensity of these pulses. So now if you add not only 3 harmonics, but let's say 10 harmonics, then you can get even shorter pulses. This is an expression of a Fourier transform or Heisenberg principle, if you want. If you have many harmonics, which means a broad frequency range, you can get very short pulses. So this was very interesting, and if you see why do we get attosecond duration with these high harmonics, first of all, we are at a high frequency. In order to have short pulses, you need to have short periods of light, and the period is inversely proportional to the frequency. And we are here in the extreme ultraviolet, thanks to this high harmonics. And we have a broad bandwidth thanks to this all of these harmonics, and these are the conditions to get to short pulses. But now the question is, or was, are the harmonics phase locked? Are the harmonics sufficiently phase locked? And actually, it's going to take more than 10 years to really be able to answer to this question. And it's actually my 2 colleagues that shared the Nobel Prize with me, Pierre Agostini and Ferenc Cross, that could finally answer this question and measure experimentally the duration of attosecond light pulses. In 93, there was a huge progress in understanding with what is called the 3-step model, which was proposed by Ken Kullander, Ken Schäfer, that you see on this picture, and also independently and at the same time by Paul Korkum. Maciej Levenstein, Misha Ivanov here proposed a quantum formulation of this 3-step model. So this model is presented on this cartoon that you see here. What is represented is an atomic potential which is strongly deformed by the laser field, by the interaction between the laser and the electron. And this interaction leads to the fact that the wall of this potential are really deformed. The wall here becomes higher and the wall on that side become lower, and now we have a potential barrier. This implies that an electron in the ground state can now tunnel through this potential barrier, is driven away when it's outside of the potential. It's driven away by the laser field, far away. The electron is traveling several nanometers. Then the laser field change of sign, and the electron is driven back towards the atom. And then there is a certain probability for the electron to recombine back to the ground state. And in this recombination process, the energy is liberated as a light pulse. So if you look at the different possible electron trajectory, you see that the electron return slightly different times, but within 100 attosecond, and with different energies within tens of electron volts. So here you have your attosecond electron wave packet, which then becomes an attosecond light pulse. So a wave packet with a duration of 100 attosecond and a bandwidth of tens of electron volts. Let me stress that this is really a quantum phenomenon, where what you get is really due to the interference between the ground state here and part of the wave function here going away and coming back and recombining. So it's a fully coherent process. How do we go from attosecond pulses to high order harmonics? Well, here I represent what I have just described, this three-step model where an electron is going out and coming back, leading to the emission of an attosecond light pulse. And this process is repeated twice per laser cycle on one side of the atom and then on the other side, and again and again. So you get the emission of a pulse train of attosecond pulses with actually a sign flip between consecutive pulses. So we see that we describe the process in the time domain. But now you can go to the frequency domain by Fourier transform, and you recover the spectrum. You can call this a frequency comb of high order harmonics, which are separated by twice the laser frequency. So we get a spectrum of odd order harmonics. Let me say a few words about phase matching, how it happens in this process. So in order to have phase matching, this is very, very similar to phase matching in crystals. You want the phase velocity of the fundamental field, which is written here, to be equal to the phase velocity of the harmonic field, so that there is a coherent buildup of the harmonic in the nonlinear medium. How is it achieved? Well, if you look at the variation of the refractive index as a function of frequency, you have typically curves like that. And if you look at the refractive index at the fundamental frequency, it's larger than 1. We are in the visible or near infrared range of the spectrum. And the refractive index of the harmonics is typically less than 1 because we are in this ultraviolet, extreme ultraviolet part of the spectrum. So if you simply look at that, then phase matching is absolutely not achieved. Fortunately, in this process, you have also partial ionization of the medium. Some of the electrons which tunnel through the barrier actually do not come back. They ionize. So we create a few free electrons in the medium. And if we take this into account, then and we add the contribution of this free electron to the refractive index. This is this term here. This is the contribution of neutral atoms, and this is the contribution of the free electron. You see that we add a negative contribution. We lower the refractive index so that the refractive index at the fundamental frequency becomes equal to the refractive index at the harmonic frequency, and we achieve phase matching. And what is needed for this to happen is not very much. It's typically a few percent. So you see that phase matching here actually is going to limit the intensity that the atoms can see, and still we can get harmonics to a certain window, which is not very large. So you need an intensity to get a strong atomic response, a high intensity, but not too high in order to achieve phase matching, and not to ruin phase matching if you have too many free electrons. Let me just mention briefly that it's a little bit more complicated that I just mentioned. We also need to include the influence of focusing to understand phase matching. Now I'm coming to important experiment, which was the first measurement of attosecond pulses in a train. Because at that time, we understood that yes, they should be attosecond pulses, but it would be really nice to measure them. How can we measure the attosecond light pulses? And it was a difficult measurement. And the first measurement were performed by Pierre Agostini and Ferencross. Pierre Agostini managed to measure attosecond pulses in a train of pulse. So the technique that he used is called rabbit. And let me explain to you this technique. It's based on two-photon ionization, as you see here. Two-photon ionization using harmonic plus laser. This creates an electron at this energy, but also a sideband electron at this energy. Now you can also ionize the atom by absorbing the next harmonic, and you have stimulated emission of a laser photon. Here you can reach this state here by two quantum paths. This quantum path here or that quantum path. And this is the technique called rabbit, like reconstruction of attosecond beating by interference of two-photon transition. So now let's look at the signal at this sideband energy. It depends on the coherent sum between this path and this path. It's an interference process. We have two quantum paths leading to the same final states. So it's going to depend on the phase of this harmonic. There is actually an additional term which I'm going to neglect for the moment. At least it's due to the ionization process. And then you have the phase of the next harmonic. And then you have a phase due to the laser, which is delayed compared to the XUV radiation, compared to the harmonics by tau. So here you have a phase contribution, which is omega tau and minus omega tau because it's an emission process. The signal is an interference signal that you see here. And the cosine term here depends on the phase difference between the two paths, phi q plus omega tau minus phi q plus 2 minus omega tau. So you see that by studying this signal as a function of the delay, you get information on the differences between the phase of the harmonics. And this is really what I want to measure. I want to check if harmonics are phase locked. So I want to measure the variation of the phase of consecutive harmonics. Doing this measurement and then reconstructing the pulse train, Pierre Agostini showed that the emission from a gas of argon atoms was made of attosecond pulse in a train with a duration of 250 attosecond, and this was a very important measurement. Let me say a few more words about progress in laser technology. During the end of the 90s, there was really a huge progress in short pulse lasers, in making these laser pulses shorter and shorter, down to the few cycle regime, which means typically less than 10 femtosecond. And this was achieved using compression techniques, in particular the hollow fiber compression technique. You have here a photo of one of these hollow fiber. And here the idea is that you use the Kerr effect in these fibers so that you have a spectral broadening, and then you can use chirp mirrors to compress these pulses. Was also progress in controlling these few cycle pulses, and the realization that it's important to measure and control what is called the carrier envelope phase, which is the difference here between the maximum of the pulse envelope and the oscillation of the electric field, and this was achieved by the group of Ursula Keller. So using all of this technique, Ferencváros at that time in Vienna generated these harmonics using very, very short light pulses, like a few femtoseconds, and managed to get only one of these, only one attosecond pulse. So he managed to develop technique not only to measure attosecond pulse, but also to generate only one attosecond pulse. And the technique that he uses to measure this attosecond pulse is called the streaking technique. I think the principle is very simple. It's similar to Pierre Agostini method in the sense that it's a cross correlation between the electric field of the laser and the attosecond pulse, and it's based on looking at electrons, ionizing a gas and looking at electrons. So the idea here is that you create electrons by absorbing this attosecond pulse. So you create an electron in the continuum with a certain momentum, pi, or a certain energy, and then you modify this momentum because ionization happens in presence of an electric field, and so that the momentum is modified, can be changed by the momentum of the field, and this depends on when the electron is born in the continuum relative to the oscillation of the laser field. So you see here on this picture that the electron can gain or lose energy depending on the time delay between ionization and the laser cycle. So in this measurement, which is famous because it's used as logotype, the measurement this led to a pulse duration of 250 attosecond. I'm now coming to applications. This field is really going into many applications now, really going from atomic spectroscopy, a new range of a new area of chemistry, which is called attosecond chemistry, condensed matter physics, industrial applications, particular imaging of small structure using this radiation, and also a new direction which we call ultra-fast quantum dynamics, trying to look at the quantum properties of matter using these very short pulses. So I think since I think my time is not over, I will just very briefly tell you an example of what we are doing in atomic spectroscopy. And we look at a simple process, which is photoionization, the photoelectric effect, which was explained by Albert Einstein in 1905, here shown for a simple atom. So here you have light ionizing an atom, and you have a photoelectron. Now, Einstein looked at this process to try to understand the property of light, and he used the fact that light is made of photons. But now let's look at the photoelectron. I'm sure you think about this photoelectron as a particle with a certain energy or momentum and coming to a detector and click. But of course, we know that this electron is both a wave and a particle. So I think what we can do with these attosecond techniques is really now measure the wave property of this photoelectron, its amplitude and phase. So this is really the question I'm going to ask. What are the wave, even quantum property of the photoelectron? How can we do that? We can do that by interferometry. So let's take an example, which is ionization of helium in a region where you have a discrete state here, an auto-ionizing state. So think that we ionize helium, we create an electron wave packet, here in blue, and this is what I want to characterize. But again, not only the energy, but also the wave property. And this is close to a resonance, close to this discrete state, and this interaction that you see here, autoionization, is going to affect the properties of this wave packet. So here you have again a beautiful quantum phenomenon where ionization can take place either directly or via excitation to a discrete state followed by autoionization, this interaction leading to this continuum. So it's quantum interference phenomena. How do we look at the electron wave packet? By interferometry, using this beautiful rabbit technique, using another harmonic that you see here, and then absorption of a laser photon or emission of a laser photon. We create a copy of this wave packet, a little bit lower in energy, and thanks to this interferometer, we can measure both the phase and amplitude of the wave packet. And here's the result. You see the amplitude show a very strong interference effect. And we can measure the corresponding phase variation, which is a pi phase jump. So now that we can measure both the amplitude and phase of this wave packet, we also can go, so this is a phase and amplitude as a function of frequency or photon energy. So now when we have this information, we can do a Fourier transform and get the time information. We can even get more than that, because now we can try to make a time frequency representation of this very fundamental process, which is photoionization of helium atom. And here is one of these representation. This is called a Wigner distribution. So you have frequency or energy here and time on the other axis. And what you can see on this picture is that photoionization occurs first very rapidly and via this direct process. So broad in frequency and short in time. Then you have a strong interference process. When it's blue, it means that it's negative. And this is really an expression of this interference between a direct process and the indirect process via the excited state, so leading to this strong interference pattern here. And finally, at long times, it's only the photo excitation followed by autoionization that is left. So this excitation followed by autoionization that you see here. This process is narrower in frequencies and longer in time. So we can really look at a very fundamental process like photoionization in a different way than before, because we have both the amplitude information and the phase information. So I think I come now to the end of this talk. I just wanted to show you one application, and here is a photo of my research group, which is quite big now, and yeah, and also acknowledgement to the agencies financing this research. Thank you for attention.
Thank you very much for the talk, Professor Anne. It's really nice to listen to a woman talking about science. You're amazing. So we have time for questions. Students who want to do Any question? Yeah? Tem mais microfone? So before the questions, so next month we are celebrating Women in Science month in here. And we are going to hold an event called Science for Them. Ciencia por Elas is especially to talk about the importance of women in science. Could you give us a word of motivation for female students or who want to pursue the career?
Yes, I think it's very important that there are more women that do physics or engineering job or in general. And really, I would like that there are more. You can see in my research group there are about 30% women. So I think I am a little bit positive. In my 40 years of research, I have seen this number really increasing. When I started in Saclay, understand you remember, I was the only woman. But and during many years, I've been the only woman in working with men. But now it's not the case. Again, in my research group, we are 30%, and I have really seen this changing with the only woman, and then maybe 5%, 10%, 20%, now 30%. So my message here is that you should not listen to people that tell you that physics is not for women. This is not true. Don't listen to this type of comments. My second message is that I'm not saying it's easy, but if you have the right motivation, it's possible to have a family and working in science. You need to find a good partner, of course, and to have the right organization around you, whether it's the country or the family or whatever. But it's not. It's possible. And so, yes, it would be great if the number of women in science increases. Yeah.
Thank you.
Oh, all right. Well, thank you, Anne, for the talk, first of all. I'm curious on the behalf of all the undergraduate students in the university here, especially myself and a couple of my colleagues that are just got into photonics and the optics group. What would you, in your opinion, would be the sort of bleeding edge or most poignant problems to be solved in the field, both in the attosecond pulse kind of regime or in any other kind of section of photonics? What would be the most important ones?
This is a very good question. I really don't have the answer to that because I can't. I don't want to pretend that I know all photonics. There are many things which are very interesting, and photonics is a great science in general. I would like to say, and working with laser is just so enjoyable. So I don't want to say too much here. Attosecond science is really booming and progressing, and the challenge in attosecond science is to use these very short pulses into a more maybe complex system, to look at condensed matter or big molecules, and really to push this type of techniques to something to applications. There's still a lot of research to do before it really becomes useful for industry or something like that. So there is a lot to do. But I would say in general, let me say like that, choose something that you like. Don't try to see, what is the hypest or the most, just choose something that you like.
Thank you. So, para as pessoas que querem fazer pergunta e não falam inglês, temos tradutores. Quem quiser. Another question?
Hello. Given the immense challenge of measuring like such short time, such short pulses, and for many years improving and the apparatus, what keep you inspired and to pursue this research, like despite so many challenges through the years?
I think if you want to be a good researcher, you need to be very stubborn, and not to be afraid by difficulties and problems. So I don't know what kept me going, but and I'm not saying it was always easy. I had some doubts, in particular at the end of the 90s, when it was not so clear how to measure these pulses. So, but keep going. This would be my recommendation. Yeah.
But I think part of his question was how do you measure such short?
Yeah. How do? Yeah, I think I explained. I can repeat if you want, a little bit easier. Do you want me to repeat that?
So actually, yeah,
Yes?
you explain it, but there is a part that I still don't understand. Is like, how does this camera is able to follow such short pulses?
I can make a very hand-waving explanation if you want. And I'm explaining actually a cross-correlation experiment. So you have an attosecond pulse. I use my hands. You can see them, right? This is one attosecond pulse. And what we do, we actually measure this pulse. So how can you measure this pulse? You don't have any detectors, right? You can measure the pulse with itself. It's called autocorrelation, but it's very difficult for using harmonics. But so instead, what Pierre Agostini and Ferencross use is a cross-correlation experiment. Cross-correlation with the electric field that is used to generate harmonics, because you have a oscillation, short oscillations. So this is the electric field of my laser pulse. You can see that. These are the oscillations. You see that?
Yeah.
Yes? And then this is the attosecond pulse. And now I'm going to do a cross-correlation experiment. I'm going to vary the delay between the two and measure something. In that case, it was ionization, so a gas, and they look at electrons. So they measure something which depends on whether you have this situation or this situation. You can see that?
Yeah.
So they measure a signal that depends on the delay between the attosecond pulse and the field, laser field.
So you don't even need a large band photodetector.
No, you just look at electrons. Now assume that this pulse is long, like this. Okay? So now if I do the same thing, I will get a signal that does not depend on the delay, right? There's no difference if I'm here or here. Yes?
Yes.
The remote, if it's very short, then there is a huge difference. So this is the principle behind these cross-correlation measurements. So you don't need a special detector. Here in that case, they just look at electrons. But what is your detector is these cross-correlation measurements. You get that?
Yeah, yeah.
And this was done two slightly different implementation by Pierre Agostini. He used interferometry, but it's very similar, and Ferencross using streaking. In both cases, it's a cross correlation.
We have another question.
Hi, Professor. Thank
Hello.
you for your talk. My question is, when you look back at when you started learning physics, now that you are a Nobel Prize laureate, what do you consider it was the most important thing you learned about physics that inspired you to keep studying this field of knowledge?
Actually, I studied mathematics quite far. I was on my way. I have a degree for teaching mathematics. But then in the end of my studies, I decided to study physics. And I had fantastic teachers in atomic physics, quantum mechanics. Claude Cohen-Tanouji, he got a Nobel Prize in 1997 for laser cooling and trapping. And he really inspired me towards the atomic physics and quantum mechanics and the interaction between light and matter. So this was my inspiration, a fantastic teacher.
More questions? I think we also have some questions on the YouTube channel.
Yeah, we have Professor N. How do you see the future of this very short pulse, considering the evolution of the peak power of the laser, now archiving the 10 to 23 power watts by centimeter square?
For creating these very short pulses, you don't need that much. So it's kind of two different areas, very high intensity physics with these very high intensities, 10 to 23 watts per square centimeter. And then the physics of attosecond light pulses. Here you need intensities of the order of 10 to 14 watts per square centimeter. Not more, because you re in phase matching, as I explained in my talk. So it's two different areas, and in our area we don't need this high intensity, but we want to have nice lasers, short pulses, high repetition rate, and this is what has happened during the last 10 years. We have, or 20 years, we have gone from this 10 hertz of titania sapphire. Now we work at 100 kilohertz using a new laser technology based on ytterbium. So it's not that we want higher intensity, but we want better and better lasers, and they are coming. So we have much nicer laser, more compact and much better.
Yeah.
I was wondering that, considering the revolutionary character of quantum technology, if you could talk a little bit about the applications of the technology used and the knowledge you produced with your research.
Yeah, I can't. This is kind of new, and this part, I am really very excited by that. But I cannot really provide a vision. But what I find very exciting is I mean, I just show an example that we are able to measure the wave function. I mean, the father of quantum mechanics, they said, oh, you can only measure the wave function square. But now I showed you that we can measure the wave function and the time dependence of this wave function. But sometimes you cannot characterize something, an electron with a wave function, because you have it's more complicated. It's an incoherent sum, and you need to characterize your electron or your pairs of electron with density matrix. So it's more advanced quantum tools. And recently we have actually managed to measure the density matrix of a photoelectron. So this is kind of the new things we begin to look at. And it's really observing the quantum mechanical world with new tools. It's very fascinating. I don't know where it's going, so it's very difficult for me to say, oh, is this going to, I don't know what. But it's very interesting. This is the beauty of research.
As an undergrad, we study very different topics, and we often find interest in many different areas. How do you know what you really want to focus your research on, and how to control this wish to explore as many things as you want?
Yeah, I would like to say pick up something you like. Because in order to, if you want to continue if you want to do research, or actually, and it doesn't need to be in academia, it can also be in industry. I think it's important you are working on something that you like, because as it was mentioned before, there will be problems, there will be difficulties. So if you don't like what you're doing, it will be very difficult. So, but if you are passionate enough and stubborn enough, then it will be much easier. So pick up something that you like. This would be my recommendation. Then I want to add that a career, it's also opportunities. In my case, I was very interested by this atomic physics and this interaction between light and matter. But this professor, Claude Tanucci, was laser cooling. But then I had a chance to do an internship at the Commissariat Énergie Atomique. And this was about atoms in strong laser field. This looked a little bit exotic. It looked a little bit, it looked close to what I was interested, but it was kind of opportunity. And after this internship, I was offered a thesis position, and this is how I continue. It's not that I really choose this and I knew that it would go to attosecond pulses. Of course not. It's kind of opportunity and then a bit of luck. Yeah.
Temos mais pergunta?
I hope you don't mind asking like a slightly different topic of question, but as you study and deepen your knowledge in physics, do you find that it strained your or the belief in God, or it does lead to a different direction? Yeah.
I think I'm not going to answer this question because I think it's very personal.
Okay, yeah.
And I also know that I know I have very good friends, physicists that are believe in God very, very strongly, and I also know others that don't. So I think it's a different type of question. It's for me, it's two different words. Yeah.
Yeah, sorry. Another question? Last one?
Hi, Professor. Thank you for the talk. As you said about opportunities, I would like to know if your lab is open to give us Brazilian students, Latino students, opportunity to visit, to know about your work and other things.
I would say our door is open. Now there are questions like financing and position and stuff like that. But in general, we and in our group, we really have can even go back to the picture of my group. It's a very multinational. It's mostly European, I must say, but really only a very small fraction is from from Sweden. So you have France, Italy, Spain, you have China, you have someone from India. So it's very multinational, and one from Portugal. No one from South America at the moment, but sometimes we do have from Mexico. Never from Brazil, actually, but maybe it will come. Yeah.
Thank you.
Okay, so Professor Anne, thank you very much for your time, for your dedication, for everything, accepting the invitation. We would like to ask you if we can take a photo with you.
Yeah, sure, sure.
Everybody can come, actually,
Yes.
if you want to take a photo. So let's sit over here.
I guess I should remove my background, but I blur it.
Só fiquem perto. Pode ir.
Vamos subindo aqui no...
Rafa, seu microfone funciona? Organiza aí.
Pessoal, vamos se alocando aqui na passarela, aqui em cima no palco. Aí quem estiver no palco, abaixa um pouquinho, por favor.
So, se abracem, se aglomerem. Agglomeration, please.
Se vocês puderem tirar uma com a gente aqui também depois, seria legal.
Boa, boa.
Corre, Vini.
So, how long? 5? Yeah. Thank you. Thank you very much, Professor.
Thank you, and yes, I hope I can visit you in Rio sometime.
Okay,
Yeah.
Anne, it was very nice to see you. Bye-bye.
Bye-bye.
Obrigada, Professor Anderson.
Bye, thank you.
Obrigado. Yeah.
Nada, tchau.
Yes,
Obrigado.
sim. How do we do
Okay.
that? The photo of the spy.